When a coin is tossed, the maximum number of possible outcomes is 2. We will get either a head or a tail. When 2 coins are tossed simultaneously, the number of possible outcomes is 4. Similarly, the number of possible outcomes increases to 8 when 3 fair coins are tossed simultaneously. The set of all the possible outcomes of a random experiment is called a sample space and is denoted by S. Each outcome in a sample space is called a sample point. So, the sample space for the experiment when 3 fair coins are tossed simultaneously is the set of all the possible outcomes. Here, each sample point is equally likely. Since the coin is fair, the probability of each sample point in the sample space is 1/8. Let A be an event that at least 2 tails appear. That is, 2 or more than 2 tails appear. Then, the sample points in event A are HTT, THT, TTH, and TTT. The probability of event A is the sum of the probabilities of its sample points, which is equal to 1/2. Consider another event, B, where the first coin shows a head. The sample points of event B are HTT, HHT, HTH, and HHH. The probability of event B is equal to the sum of the probabilities of its sample points. This is also equal to 1/2. Observe that the sample point HTT is common to both the events A and B. This implies that event A intersection B has one element, that is, HTT. The probability of event A intersection B is 1/8. We just calculated the probabilities of events A and B, considering that they happen independently. Suppose we have to find the probability of A if event B has already occurred. In such a case, the sample space for event A will be the set of sample points of event B. In other words, event A is a new random experiment for which the sample space is the set of all the favorable outcomes to the occurrence of event B. And event A is the appearance of at least 2 tails. Therefore, the sample point of B favorable to the occurrence of event A is HTT. The number of sample points in the sample space of event B is 4, and all are equally likely. Therefore, the probability of each sample point is 1/4. It implies that the probability of event A is 1/4. Here, the probability of event A is called the conditional probability of A given that event B has already occurred. This is denoted as shown and is read as the probability of A given B. Observe that the sample point of event A, given that event B has already occurred, is common to both event A as well as event B. Or, the outcomes of event A are the sample points of event A intersection B. Thus, the conditional probability of A given B can also be written as the number of elementary events favorable to event A intersection B divided by the number of elementary events favorable to event B. this is equal to the cardinal number of A intersection B divided by the cardinal number of B. On dividing the numerator and the denominator by the cardinal number of S, we get the probability of event A intersection B divided by the probability of event B. Mathematically, conditional probability is defined as if A and B are two events of the same sample space S, then the conditional probability of event A given that event B has occurred is given by the probability of A given B is equal to the probability of A intersection B divided by the probability of B, where the probability of B is not equal to 0. Let's apply this result to find the probability of the previous experiment in which the sample space and events A and B are given as shown. Here, we need to find the probability of A if event B has already occurred. Now, event A intersection B is the set of the sample points common to both the events A and B, which is HTT. Now, the probability of the occurrence of event A intersection B in sample space S is equal to 1/8, and the probability of the occurrence of event B is equal to 4 divided by 8, which is equal to 1/2. Therefore, the probability of A given B is equal to 1/8 divided by 1/2. On simplification, we get the probability of A given B as 1/4. Note that the definition of conditional probability can also be applied in a general case, where the elementary events are not equally likely. Let's now discuss the properties of conditional probability. The first property says, if A is an event associated with sample space S, then the probability of S given A is equal to the probability of A given A, which is equal to 1. We know that the probability of S given A is equal to the probability of S intersection A divided by the probability of A. Since A is a subset of S, S intersection A is A. Thus, the probability of S intersection A is equal to the probability of A. Therefore, the probability of S given A is equal to 1. Next, the probability of A given A can be written as the probability of A intersection A divided by the probability of A. We know that A intersection A is equal to A. Thus, the probability of A divided by the probability of A is equal to 1. Hence, the probability of S given A is equal to the probability of A given A, which is equal to 1. The next property says that if A and B are two events of sample space S, and E is an event of S such that the probability of E is not equal to 0, then the probability of A union B given E is equal to the probability of A given E plus the probability of B given E minus the probability of A intersection B given E. Let's consider the left-hand side of the equation. By the definition of conditional probability, this can also be written as the probability of A union B intersection E divided by the probability of E. By the distributive law of union of sets over intersection, the numerator becomes the probability of A intersection E union B intersection E divided by the probability of E. On simplification, we get the probability of A given E plus the probability of B given E minus the probability of A intersection B given E. This is the right-hand side of the property. Hence, the property is verified. We know that for two disjoint events A and B, A intersection B is a null set. This implies that the probability of A intersection B given E is equal to 0. Therefore, the probability of A union B given E is equal to the probability of A given E plus the probability of B given E if A and B are disjoint sets. Another property says that if A and B are two events of sample space S, then the probability of A complement given B is equal to 1 minus the probability of A given B. We know the probability of S given B is equal to 1. This implies the probability of A union A complement given B is equal to 1, since union of A and its complement is equal to S. Events A and A complement are two disjoint events. Thus, we get the probability of A given B plus the probability of A complement given B is equal to 1. Therefore, the probability of A complement given B is equal to 1 minus the probability of A given B. We know that if E and F are two events in same sample space S, then the conditional probability of event E given that event F has occurred is given by the probability of E given F is equal to the probability of E intersection F divided by the probability of F, where the probability of F is not equal to 0. This implies that the probability of E intersection F is equal to the probability of E given F multiplied by the probability of F. Similarly, the conditional probability of F given that event E has occurred is equal to the probability of F intersection E divided by the probability of E, such that the probability of E is not equal to 0. Now, F intersection E is equal to E intersection F. This implies the probability of E intersection F is equal to the probability of F given E into the probability of E. From 1 and 2, we get the probability of E intersection F is equal to the probability of E given F into the probability of F. This is further equal to the probability of F given E into the probability of E. This is called the multiplication rule of probability. Let's now look at an example. Consider a pack of cards. Two cards are drawn one after the other without replacing the first card back into the pack. Suppose the first card drawn from the pack is a king, and the second card drawn is a queen. Then, what would be the probability of the event? Let K and Q be the events of drawing a king and a queen card, respectively. As we need to find the probability of drawing two cards one after the other, without replacement, we have to find the probability of K intersection Q. Now, there are 4 king cards in a pack of 52 cards. So, the probability of drawing a king card is 4 divided by 52. The card drawn is not replaced. This implies that the number of cards available for the second draw is 51. Thus, the probability of drawing a queen card, given that the first draw is a king card, is 4 divided by 51, because there are 4 queen cards present in 51 cards. From the multiplication rule of probability, we have the probability of K intersection Q is equal to the probability of Q given K into the probability of K. Substituting the values of the probability of Q given K and the probability of K in the rule, we get 4 divided by 663. Therefore, the probability of K intersection Q is equal to 4 divided by 663. Hence, the probability of first drawing a king card and then a queen card is 4 divided by 663. This multiplication rule can be extended to more than 2 events. For example, for 3 events E, F and G in sample space S, the multiplication rule is defined as the probability of E intersection F intersection G is equal to the probability of E into the probability of F given E into the probability of G given E intersection F is equal to the probability of E into the probability of F given E into the probability of G given EF. Let's consider an example. An urn contains 12 red balls and 8 blue balls. Suppose we take 2 red balls and then a blue ball one after another without replacement. What would be the probability of the event of taking 2 red balls and a blue ball? Let R be the event of taking a red ball from the urn. Let B be the event of taking a blue ball from the urn. The total number of balls available in the urn is 12 red balls plus 8 blue balls, which is equal to 20 balls. First, a red ball is drawn. And since there are 12 red balls, the probability of taking a red ball is 12 divided by 20, which is equal to 3 divided by 5. Since the ball drawn is not replaced in the urn, 11 red balls are now available, and the total number of balls is 19. Now, the probability of taking another red ball is given by the probability of R given R is equal to 11 divided by 19. Since another red ball is drawn, the total number of available balls in the urn is 19 minus 1, which is equal to 18. Therefore, the probability of taking a blue ball with the condition that 2 red balls have already been taken is given by the probability of B given RR. This is equal to 8 divided by 18, or 4 divided by 9. From the multiplication rule for 3 events, we have the probability of RRB is equal to the probability of R into the probability of R given R into the probability of B given RR. Substituting the values of the probability of R, probability of R given R, and the probability of B given RR, we get the expression as shown. On simplifying, we get 44 divided by 285. Therefore, the probability of RRB is equal to 44 divided by 285. Hence, the probability of taking two successive red balls and a blue ball is equal to 44 divided by 285. Let's perform an experiment. Draw a card from a deck of 52 playing cards. Assuming that each event of the experiment is equally likely. Let E and F be two events, where E is the event that the card drawn is a heart, and F is the event that the card drawn is an ace. You know there are 13 hearts and 4 aces in a deck of cards. Therefore, the probability of event E is 13 divided by 52, or 1/4. Similarly, the probability of event F is 4 divided by 52, or 1 divided by 13. Now, there is one card that is common to both the events. So, E intersection F is the card, and it is the ace of hearts. And since there is only one ace of hearts in a deck of 52 playing cards, the probability of event E intersection F is 1 divided by 52. The conditional probability of event E, given that event F has occurred, is equal to the probability of E intersection F divided by the probability of event F. The probability of E intersection F is 1 divided by 52, while the probability of F is 1 divided by 13. On simplification, we get 1/4. This is equal to the probability of event E. This implies that the probability of E is not affected by the occurrence of event F. Now, the conditional probability of event F, given that event E has occurred, is equal to the probability of E intersection F divided by the probability of event E. This is equal to 1 divided by 52 whole divided by 1 divided by 4. On simplification, we get 1 divided by 13, which is equal to the probability of event F. Therefore, the conditional probability of event F given E is equal to the probability of event F. This implies that the probability of F is not affected by the occurrence of event E. Observe that in both the cases, the probability of occurrence of one event is not affected by the occurrence of the other event. Such events are called independent events. Events E and F are said to be independent events if the probability of the occurrence of one event is not affected by the occurrence of the other event. Mathematically, two events E and F are said to be independent events if the probability of E given F is equal to the probability of E, where the probability of F is not equal to 0. Similarly, the probability of F given E is equal to the probability of F, where the probability of E is not equal to 0. Recall the multiplication rule of probability. It states that the probability of E intersection F is equal to the probability of E given F into the probability of F. If events E and F are independent events, then the probability of E given F is equal to the probability of E. Thus, the probability of E intersection F is equal to the probability of E into the probability of F. This discussion leads us to a definition of independent events. Events E and F are said to be independent events if the probability of E intersection F is equal to the probability of E into the probability of F. Two events E and F are said to be dependent if the probability of E intersection F is not equal to the probability of E into the probability of F. Three events E, F and G are said to be mutually independent if the probability of E intersection F is equal to the product of the probabilities of events E and F. The probability of E intersection G is equal to the product of the probabilities of events E and G. The probability of F intersection G is equal to the product of the probabilities of events F and G. And the probability of E intersection F intersection G is equal to the product of the probabilities of events E, F, and G. Let's now look at some properties of independent events. If E and F are two independent events associated with some experiment, then E and F complement are also independent. Let's verify this property. It is given that the probability of E intersection F is equal to the probability of E into the probability of F, since they are independent events. Here, we have to prove that the probability of E intersection F complement is equal to the probability of E into the probability of F complement. Let's begin with the proof. It is clear from the Venn diagram that events E intersection F and E intersection F complement are mutually exclusive. Also, E is equal to E intersection F union E intersection F complement. Thus, the probability of E is equal to the probability of E intersection F plus the probability of E intersection F complement. This can also be written as the probability of E intersection F complement is equal to the probability of E minus the probability of E intersection F. Since events E and F are independent, the probability of E intersection F is equal to the product of the probabilities of events E and F. Taking the probability of E common from the right-hand side, we get the expression as shown. Now, 1 minus the probability of F is equal to the probability of F complement. Therefore, the probability of E intersection F complement is equal to the probability of E into the probability of F complement. Hence, events E and F complement are also independent events. Similarly, it can be proved that E complement and E complement and F complement are also independent. If E and F are two independent events associated with some experiment, then the probability of the occurrence of at least one of E and F is given by 1 minus the product of the probabilities of E complement and F complement. Let's verify this property. It is given that E and F are independent events, and therefore, the probability of E intersection F is equal to the probability of E into the probability of F. we have to show that the probability of E union F is equal to 1 minus the probability of E complement into the probability of F complement. The probability of at least one of E and F, or the probability of E union F, is equal to the probability of E plus the probability of F minus the probability of E intersection F. Since events E and F are independent events, the probability of E intersection F is equal to the probability of E into the probability of F. Let's take the probability of F as common from the last two terms of the right-hand side. 1 minus the probability of E is equal to the probability of E complement. The probability of E can also be written as 1 minus the probability of E complement. Taking the probability of E complement as common again, we get 1 minus the probability of E complement multiplied by 1 minus the probability of F on the right-hand side. Since 1 minus the probability of F is equal to the probability of F complement, we get 1 minus the probability of E complement into the probability of F complement on the right-hand side. Hence, the probability of at least one of E and F is equal to 1 minus the probability of E complement into the probability of F complement. Here are two baskets. There are 2 apples and 3 oranges in basket 1 and 3 apples and 5 oranges in basket 2. The probability of drawing an orange from basket 1 is 3/5, and the probability of drawing an apple from basket 2 is 3/8. In both the cases, the fruit drawn is given and the basket from which the fruit is drawn is also given. Suppose an apple is drawn at random from one of the baskets. Can you find the probability that the apple is drawn from basket 1? To solve such types of problems, in 1763, a mathematician, Thomas Bayes, developed a new formula by using conditional probability. This new formula is called Bayes' theorem. Before proving the theorem and discussing it in detail, let's look at some definitions and basic theorems. Consider an experiment of tossing 3 coins simultaneously. The sample space of the experiment has 8 outcomes, which are as shown here. Consider 3 events, A, B, and C, where event A is defined as getting at least 2 heads. Event B is defined as getting exactly 2 tails. And event C is defined as getting 3 tails. From these 3 events, it is clear that events AB, events AC, and events BC are disjoint, and the union of events A, B, and C is sample space S. The probability of event A is 1/2, event B is 3/8, and event C is 1/8. The set of such events A, B, and C of a sample space is a partition of the sample space. Again, let's consider another event, E, of sample space S, defined as getting a head in the first coin. The complement of event E is E' as shown. We know that an event and its complement are always disjoint, and their union is equal to the same sample space. Since events are non-empty, the probabilities of events E and E' are also greater than 0. Again, this shows that events E and E complement together represent another partition of sample space S. Likewise, we can have any number of partitions of a sample space. In general, a set of events E1, E2, E3, and so on till En represents a partition of sample space S if they are pairwise disjoint. The union of the events is the sample space itself, and the probability of each event is greater than 0. Next, let's discuss the theorem of total probability, which is based on the partitions of a sample space. Let the set of events E1, E2 and so on till En be a partition of sample space S, and suppose that each of the events E1, E2 and so on till En has non-zero probability of occurrence. Let A be any event associated with S. Then the probability of A is equal to the summation of the product of the probability of Ej and the probability of A given Ej, where j is running from 1 to n. Given that the set of events E1, E2 and so on till En is a partition of sample space S, by the definition of partition, sample space S is equal to the union of all the events in the partition. The events are pairwise disjoint. Also, the probability of each event is greater than 0. Now, for any event A associated with sample space S, A is equal to A intersection S. Since S is the union of all the events of the partition, A is equal to A intersection, the union of all the events. Now, by the distributive law of intersection over the union, A is equal to the union of A intersection E1, A intersection E2, and so on till A intersection En. From the figure, A intersection EI is a subset of EI. Similarly, A intersection EJ is a subset of EJ. Also, the events are pairwise disjoint. This implies that any pair of events EI and EJ are disjoint, for I is not equal to j. Therefore, A intersection EI and A intersection EJ are also disjoint for all I is not equal to j, and j is equal to 1, 2, 3, and so on till n. Thus the probability of A is equal to the probability of the union of A intersection E1, A intersection E2, and so on till A intersection En. This is equal to the sum of the probabilities of A intersection E1, A intersection E2, and so on till A intersection En. Now, by the multiplication rule of probability, we get the probability of A as shown. This can also be written as the summation of the probability of Ej into the probability of A given Ej, where j is running from 1 to n. Hence the theorem is proved. Let's now state and prove Bayes' theorem. Bayes' theorem states that if E1, E2 and so on till En are n non-empty events that constitute a partition of sample space S, that is, the events are pairwise disjoint and the union of events is equal to S, and A is any event of non-zero probability, then the probability of EI given A is equal to the probability of EI into the probability of A given EI, whole divided by the summation of the probability of Ej into the probability of A given Ej for all I is equal to 1, 2, 3 and so on till n, and j is running from 1 to n. It is given that the events E1, E2 and so on till En is a partition of sample space S. This implies that the events are pairwise disjoint, and the union of the events is equal to sample space S. It is also given that A is a non-empty event associated with S. Now, by the formula of conditional probability, the probability of any event of the partition EI given event A has already occurred is equal to the probability of A intersection EI divided by the probability of A. By the multiplication rule of probability, the numerator, the probability of A intersection EI, can be written as the probability of EI into the probability of A, given event EI has already occurred. Since A is a non-empty event associated with sample space S, and events E1, E2 and so on till En forms a partition of S, then by the theorem of total probability, the denominator P of A is equal to the summation of the probability of Ej into the probability of A given Ej, where j is running from 1 to n. Hence, Bayes' theorem is proved. Sometimes, Bayes' theorem is called the formula for the probability of causes. In Bayes' theorem, events E1, E2 and so on till En are called hypotheses. The probability of EI is called the priori probability of hypothesis EI. The probability of EI given A is called the posteriori probability of hypothesis EI. Let's get back to the example we considered in the beginning. There are 2 apples and 3 oranges in basket 1 and 3 apples and 5 oranges in basket 2. Suppose an apple is drawn at random from one of the baskets. Let's find the probability that the apple is drawn from basket 1. Let B1 and B2 be the events of choosing baskets 1 and 2 respectively. Since the events are equally likely, the probability of choosing each basket is 1/2. Let E be the event of drawing an apple from the baskets. The probability of drawing an apple, given that basket 1 has already been selected, is the number of apples in basket 1 divided by the total number of fruits in it, which is equal to 2/5. The probability of drawing an apple, given that basket 2 has already been selected, is the number of apples in basket 2 divided by the total number of fruits in it, which is equal to 3/8. Now, the probability of drawing a fruit from basket 1, given that the drawn fruit is an apple, is the probability of B1 given E. Now, by applying Bayes' theorem, we have the probability of B1 given E is as shown. On substituting the values and simplifying, we get 16 divided by 31. Hence, the probability that the drawn apple is from basket 1 is equal to 16 divided by 31. We know that the results of an experiment can be the same or can vary if we perform the same experiment a number of times. For example, the sum of the measures of the angles of a quadrilateral is 360 degrees. Consider the quadrilaterals shown here. Let's measure the angles of the quadrilaterals using a protractor. On adding all 4 angles of each quadrilateral, we see that the sum is 360 degrees, and that this is true for all quadrilaterals. Thus, in such types of experiments, the result can be predicted, and it will be the same for any number of trials. In the counterpart, let's look at another example, where a die is rolled 10 times. The possible results are 1, 2, 3, 4, 5, and 6. Here, it is quite impossible to predict the result if the die is rolled once again. It could be any number from 1 to 6. Such experiments are called random experiments. Mathematically, a random experiment is an experiment that has more than one possible result, and it is not possible to predict the result in advance. The result of each trial is called an outcome, and the collection of all such possible outcomes is called the sample space. Many a times, we want to know how many times an outcome occurs in an experiment. For example, in tossing 2 coins, we may want the number of heads that appear. In rolling 2 dice, we may want the sum of the numbers on the 2 dice. In an experiment of drawing 3 balls at random from an urn containing 6 blue and 7 red balls, we may want to know the number of blue balls in the sample of 3 balls. In all the cases, a rule can be assigned to each outcome of the experiment, so that the outcome is a real number. For example, in the first example, the number of heads that appear in an outcome could be 2, 1, or 0. Similarly, in the second example, the sum of the numbers in an outcome could be 2, 3, 4, and so on till 12. In the third example, the number of blue balls in an outcome could be 0, 1, 2, or 3. In all the cases, the real number associated with each outcome is not fixed. This real number varies depending on the different outcomes of the experiments. In other words, this value depends on the random experiment, and hence it is called a random variable. Generally, it is denoted by the capital letter X. Let's review again the experiment in which 2 coins are tossed. The outcomes are HH, HT, TH, and TT. Thus, the sample space of the experiment is as shown. Let's assign a rule, the number of heads that appear. If X denotes the number of heads that appear, then the number of heads that appear in outcome HH or X of HH is 2, X of HT is 1, X of TH is 1, and X of TT is 0. Similarly, we can also define another rule, the number of tails that appear by a random variable y. The value of y for each outcome is shown. Likewise, for a random experiment, we can define many rules. We can compare random variable x with a function whose domain is the set of outcomes or the sample space of a random experiment. And the codomain is the set of real numbers, because x can take only real numbers. Hence, a random variable can be defined as a real valued function whose domain is the sample space of a random experiment. Consider 6 bowls, namely B1, B2, B3, B4, B5, and B6. Let these bowls have 3, 5, 4, 4, 6, and 5 marbles respectively. Let x be the random variable that represents the number of marbles in the bowl selected. If bowl B1 is selected at random, then x of B1 is equal to 3. If bowl B2 is selected at random, then x of B2 is equal to 5. Similarly, x of B3 is equal to 4. X of B4 is equal to 4. X of B5 is equal to 6, and x of B6 is equal to 5. Thus, x can take any value from 3 to 6 depending upon the bowl selected. Hence, x takes the value 3 when bowl B1 is selected. X takes the value 4 when bowl B3 or bowl B4 is selected. X takes the value 5 when bowl B2 or bowl B6 is selected. X takes the value 6 when bowl B5 is selected. If we assume that each bowl is equally likely to be selected, then the probability of selecting a bowl is 1/6. That means the probability that bowl B1 is selected is 1/6. Or the probability that X can take the value 3 or P of X equal to 3 is 1/6. The probability that X can take the value 3 is equal to the probability that a bowl with 3 marbles is selected, which is equal to 1/6. Similarly, the probability that bowl B3 or bowl B4 is selected is 2/6. This implies that the probability that X can take the value 4 or P of X equal to 4 is equal to 2/6. In other words, the probability that X can take the value 4 is equal to the probability of selecting a bowl with 4 marbles, which is equal to 2/6. Similarly, the probability that X can take the value 5 is equal to the probability of selecting a bowl with 5 marbles, which is equal to 2/6. And the probability that X can take the value 6 is equal to the probability of selecting a bowl with 6 marbles, which is equal to 1/6. Let's arrange the values of the random variable X and the corresponding probabilities in tabular form as shown here. This table is called the probability distribution of random variable X. In general, the probability distribution of random variable X is the system of numbers x1, x2, x3 and so on up to xn, along with the corresponding probabilities. P of X is equal to P1, P2, P3 and so on up to Pn, where every probability is greater than 0, and the sum of the probabilities is equal to 1. Now, xi is a possible value of random variable X, and the statement random variable X is equal to xi is true for some points of the sample space. Hence, the probability that X can take the value xi is always greater than 0. Also, X takes all sample points of a sample space, and hence the sum of all the probabilities is equal to the probability of the sample space, which is equal to 1. Hence, the sum of the probabilities in a probability distribution must be 1. Consider an experiment of tossing 3 coins simultaneously. The sample space associated with this experiment has 8 outcomes that are as shown. Let X be a random variable denoting the number of heads that appear in each outcome. From the sample space S, it is clear that the possible values of X are 0, 1, 2, or 3 heads. Therefore, the probability distribution of random variable X can be presented as shown here. Many a times, we may need to describe the characteristics of the random variable by means of a single number. Mean is such a number, which is computed from the probability distribution of the random variable. Mathematically, mean is the middle or average value of a random variable. It is denoted by the symbol mu. Mu is equal to the sum of the products of the possible values of X and their respective probabilities, where xi's are the possible values of X and pi's are their respective probabilities. The mean of random variable X is also called the expectation of X and is denoted by E of X. Therefore, the expectation of X or mean of X can be expressed as shown. Let's find the mean of x for the probability distribution that we arrived upon earlier. Now, the mean of x is equal to x1 into p1 plus x2 into p2 plus x3 into p3 plus x4 into p4. On substituting the values of x and their respective probabilities, we get the expression as shown. On simplification, we get 12 divided by 8. Hence, the mean of random variable x is 1.5. Take a look at the probability distributions of two experiments. In the first distribution, the possible values of random variable x are 0, 1, 2, and 3. Their respective probabilities are 1/8, 3/8, 3/8, and 1/8. In the second distribution, the possible values of random variable y are -1, 0, 3, 5, and 6. Their respective probabilities are 2/8, 3/8, 1/8, 1/8, and 1/8. Let's calculate the mean of the random variables in both the cases. The mean of random variable x in the first distribution is 1.5. The mean of random variable y in the second distribution is 1.5. Observe that both the distributions have the same mean. However, it does not give us any information about the variability in the values of the random variables. To understand the variability in the variables, let's draw two graphs using the distributions by taking the values of the random variables along the x-axis and their probability along the y-axis. From the figures, it is clear that the spread or scatter of the values of x is uniform, while the spreading among the values of y is not uniform. In statistics, we know that variance is a measure of the spread or scatter in data. Similarly, variance can be considered as the measure of the spread of the values of a random variable in a probability distribution. In a probability distribution of random variable x, the variance of x is given by the formula sigma x squared, which is equal to the summation of xi minus mu whole squared multiplied by p of xi, where I is running from 1 to n, and x1, x2, x3, and so on till xn are the possible values of x, and they occur with the probabilities p of x1, p of x2, p of x3, and so on till p of xn respectively. Mu is the expectation of x or mean of x. The formula can also be written as sigma x squared is equal to e of x minus mu whole squared. The square root of the variance of random variable x is called the standard deviation of random variable x. The formula for standard deviation is shown here. Now, we'll find the variances of the given probability distributions as follows. The variances of the probability distributions are 0.469 and 6.749. This implies that the variance of random variable y is more than the variance of random variable x. Thus, we can say that the spread of values is more in y than in x. Let's review the formula for the variance of variable x again. Now, we'll expand xi minus mu whole squared. On simplifying, we get the expression as shown. Since mu is a constant, we take out mu squared in the second term and 2 mu in the third term in the summations. We know that the sum of the probabilities in a probability distribution is 1. The mean of a random variable is equal to the sum of the products of the possible values of the variable and the probability of their occurrence. Thus, the expression becomes as shown. On substituting the formula of mu, we get this expression. Let's represent it in its function form. Therefore, the variance of x is equal to e of x squared minus the square of e of x. This is the alternate formula to find the variance of a probability distribution. Let's look at the trials associated with some random experiments. A coin is tossed. Roll a die and determine whether it is a 6. A fruit selected from a basket can be spoiled or not spoiled. Is a candidate selected for the MBBS course? Is the newborn child a girl? Let us now observe each experiment carefully. In the first experiment, the output can be either a head or a tail. When a die is rolled, getting a 6 can be either yes or no. In a fruit basket, the selected fruit can be either a spoiled one or a good one. A candidate can be selected for the MBBS course depending upon his or her performance in the entrance test. Thus, the answer to the question can be either yes or no. The newborn child can be either a girl or a boy. Thus, the answer to the question can be either yes or no. Observe that in each of the cases, there are only 2 possible outcomes. Let one of the outcomes be called a success. For convenience, the happening or occurrence of a trial is considered a success. Similarly, the other outcome is considered not a success or a failure. For example, in the first experiment of tossing a coin, if the occurrence of a head is considered a success, then the occurrence of a tail is a failure. If we perform this experiment any number of times, then each trial will have only 2 outcomes, success and failure. This means that these trials are independent, and hence the outcome of one trial is independent of the outcome of the others. Such independent trials having only 2 outcomes, namely success and failure, are called Bernoulli trials. In other words, the trials of a random experiment are said to be Bernoulli trials if they satisfy some conditions. The number of trials should be finite. The trials should be independent. Each trial must have exactly 2 outcomes, success and failure. The probability of success remains the same in each trial. Let's use this definition to verify whether a trial is a Bernoulli trial. Consider an experiment of throwing a fair die 10 times. Let's verify if the trials of the appearance of 2 on a die are Bernoulli trials. Let the event of getting a 2 in each trial be defined as success. Let the probability of success be P. Clearly, the successive throws are independent. Therefore, the probability of success in the first throw is 1/2. The probability of success in the second throw is also 1/2. Similarly, the probability of success remains the same for the other 8 throws. Hence, the trials of getting a 2 are Bernoulli trials. Consider an experiment of tossing a coin. Let the occurrence of a head be considered a success, and the occurrence of a tail a failure. Thus, the probability of success is 1/2, which remains the same for any number of trials. This implies that the outcome of each trial is independent. Hence, the trials are Bernoulli trials. Many a times, we wish to know the probability of a certain number of successes in Bernoulli trials. The outcome of having one success in one trial is S. The outcomes having one success in 2 trials are SF and FS. The outcomes having 2 successes in 3 trials are SSF, SFS, and FSS. It seems easy to know the possible outcomes associated with a less number of trials. However, it becomes quite tedious and time-consuming as we go for higher number of trials. Now, let's derive a formula to avoid this time-consuming calculation. Let X denote the number of successes in a trial, where a success denotes the occurrence of a head. Let P and Q denote the probabilities of getting a success and a failure, respectively. Let's begin by tossing the coin once. The possible outcomes are S and F. Here, the number of successes is either 0 or 1. Therefore, the probability that X can take the value 0 is the probability of the occurrence of a failure, which is Q. And the probability that X can take the value 1 is the probability of the occurrence of a success, which is P. So, the probability distribution of X is as shown. Next, let the coin be tossed twice. In this case, the possible outcomes are SS, SF, FS, and FF. Here the number of successes is 0, 1, or 2. Therefore, the probability that X can take the value 0 is the probability of the occurrence of FF, which is Q squared. The probability that X can take the value 1 is the sum of the probabilities of the occurrences of SF and FS, which is 2PQ. The probability that X can take the value 2 is the probability of the occurrence of SS, which is P squared. Therefore, the probability distribution of X when the coin is tossed twice is as shown. Now, let's consider the case when the coin is tossed thrice. The possible outcomes are SSS, SSF, SFS, FSS, SFF, FSF, FFS, and FFF. The number of successes in this case is 0, 1, 2, or 3. Therefore, the probability that X can take the value 0 is the probability of the occurrence of FFF, which is Q cubed. The probability that X can take the value 1 is the sum of the probabilities of the occurrences of the events having one success, which is 3pq squared. The probability that x can take the value 2 is the sum of the probabilities of the occurrences of the events having 2 successes, which is 3p squared q. The probability that x can take the value 3 is the probability of the occurrence of SSS, which is p cubed. Therefore, the probability distribution of x when the coin is tossed thrice is as shown. Observe that the distribution of x for the Bernoulli trials are similar to the binomial expansions of q plus p raised to the power of n. For the first trial, the power is 1. For the second trial, it is 2. And for the third, it is 3. Also, the probabilities of 0, 1, 2, or 3 successes are the corresponding first, second, third, and fourth terms of the respective binomial expansions. This result can be extended to n Bernoulli trials. In an experiment of n Bernoulli trials, the probabilities of 0, 1, 2, and so on till n successes are the first, second, third, and so on till n plus 1th terms of the expansion, q plus p whole raised to the power n. The terms of the binomial expansion of q plus p whole raised to the power n are shown. This probability distribution of a random variable x is called a binomial distribution. Thus, the general formula for the probability of a given number of successes is given by the probability of x successes, or the probability that x can take the value x, is ncx into q raised to the power n minus x into p raised to the power x. This is denoted by p of x. Now, ncx can be written as n factorial divided by x factorial into n minus x factorial, where x is equal to 0, 1, 2, and so on till n, and q is equal to 1 minus p. Here, p of x is known as the probability function of the binomial distribution. Now, let's apply binomial distribution to find the probability of getting 2 heads if a coin is tossed 6 times. Let the event of getting a head on tossing a coin be a success, and the event of getting a tail be a failure. Let x denote the number of heads obtained when a coin is tossed 6 times. Let p and q be the probabilities of getting a head and a tail, respectively, if a coin is tossed once. Therefore, p is equal to 1/2 and q is also equal to 1/2. Since the coin is tossed 6 times, the number of trials is equal to 6. Therefore, x has a binomial distribution with n is equal to 6 and p is equal to 1/2. The probability that x is equal to x is given by the formula here. Thus, the probability of getting 2 heads, or the probability that x can take the value 2, is equal to 6c2 into half raised to the power 6 minus 2 into half squared. This is equal to 6c2 into half raised to the power 6. On simplification, we get 15 divided by 64. Hence, the probability of getting 2 heads when a coin is tossed 6 times is 15